Thanks. So what I was saying is that 2 years ago, for those that were lucky enough to go to Mikai, the hot topic was Mamba. Everything was Mamba that, Mamba this, Mamba that. So I didn't go to Mikai this year, but I had a few people reporting and I had a look at the literature, and this year was foundational model. Foundation model was all over the place, and obviously we had a few Mamba foundation. But if you look at the literature, a lot of what is happening is that anything is called a foundation model. As long as you train a unit on your laptop with 3 data sets, it's becoming foundation. So what we wanted to do is to try to have a discussion amongst all of us to set the scene. So that's not the only slide we've got. So we've done more than that. There we go. So, but that's the only one where you will have me speaking. So what we've tried to do when we prep for this session is that we try to identify the building block of what will make a foundation model so that we can then expand on all of those and have a bit of an overview there. So, and we identify four different topics. Can't get rid. Nothing works today.
Well, you drag it to the side of it, that's why.
Shoot. Yeah. Oh no, it's gonna get worse. So Pablo, you're on camera, just smile all the way, you'll be fine. So we've got 4 different topics that we will be using throughout the different presentations. So on the left-hand side, you've got data. So data is the main component of what makes a foundation model. We will speak about the different pieces. Obviously, there are some architecture consideration. Maybe there is life outside of Transformer, or maybe not. We shall see. Something that's quite important is like when it comes with the scale of foundation models, and we've got issue with supervised learning, and then there are other approach that needs to be used. So self-supervised being the obvious one, but then there are other considerations that are coming into the mix, and as well the task and the domain that are the building parts of what might or might not make a foundation model. So we are going to follow these 4 different points. And when I say we, that's mostly not me. I can't even get a pointer to work, so here we are. And that's my laptop, which makes it even worse. So yeah, so we will cover four topics with 5 different people. So first, Praj, next to me now, is going to give a bit of the context of where are the definition coming from, what they mean, how things have been evolving over time, a bit of a highlight on the legislation part, so that then David will be then able to expand on the building blocks, going into a bit more detail on everything that I was mentioning, so like what architecture are there, what are the data that are used, what are the training regimes that are used, what are the specificities, and as well looking into the task, what makes a model different from a product, and all these type of things. Then we thought that we are mostly doing vision, so Dino is something that is extremely popular. So we thought that would be a good opportunity to dive into this one, trying to understand what is actually specific, what makes Dino slightly different from a standard of it. So is it from the architecture? Is it from the training? Is it from the data? Is it everything bundled together? And then, I mean, there is always 2 faces to a coin, so it's not all rosy, and it's very likely that foundation models are not going to work for everything and anything. It might not be the Swiss Army knife that a lot of people are hoping it is. And then we will have Julien and Yann in the opposite order. Yann and Julien that are going to present pitfalls. Is there any bias? Are there any issues? And as well focusing as well of what is happening on the healthcare side. So I said I wouldn't speak long, and I did lie, but I'm going to now hand over to Praj, that is going to give you a bit of an introduction of the concept. Oh, he's alive! I'm back.
Cool. Thank you, Marc. Right, as Marc mentioned, so I'm going to talk about a few things about definitions. We'll talk about core aspects, some setting the scene about the historical concepts and how things have changed in terms of definition, and some idea about comparison between what is and what is not a foundation model. Then we'll go into bits and bobs about data, and then some examples in the end. Then we move on to the other aspects. So what are foundation models? So that's the classic definition we've heard from Stanford in 2021. Now the terminology is changing into large X models, although there is no papers published on it, but Wikipedia says this is the next word coming out. So that's why I put it up there. X means multimodal data. That's the reason they put it large. model that utilizes multimodal data. But the definition itself is quite broad. You can see it. So there is broad data, self-supervision, adapted, and then wide range of downstream tasks. So those are the key words in that definition. Things haven't changed with the IBM definition 2024. The only thing they added there was billions of parameters. That was an extra thing. But three main core things about foundation is scale, generality, and transferability. So we've seen scale boom up from millions to trillion now with GPT 5.2, although it's not published. And then generality, we have seen that it's been used for multiple downstream tasks, can be multimodal at the same time, or a specific task. So could be text for LLMs, but vision, classification, multimodality is the generality posed for downstream tasks for these models. And transferability, we've seen that it can be transferred with very little amount of training or fine-tuning, even zero cert has been shown. So in terms of evolution, that's the table there on the side, started from BERT. In the same year, there was MOCO and SimCLR producing the contrastive self-supervised learning. And then as you go along, they figured out that we have to term this as a word. So they came up with foundation models in 2021. If you move down further, you've seen CLIP came up, the masked autoencoders came up in 2022, and then GPT-4 with Dino coming in the same time from Vision side. So 2025 was Dino v3 as a whole, along with GPT-5. And then that was the end in 2025. We can see some medical adaptation of that group of foundation models. In terms of legality, so I think that came up a few years down the line after it was defined. And the reason mainly was because of the potential security risk or serious risk these models posed. And that compounded into producing some acts, regulations by EU, UK producing some reports about it. But the definition largely is the same thing. The only thing different here is the US definition that says it has to be at least 1 billion parameters, which we don't agree because there's lots of models that are still less than 1 billion. But that's what they have set as a definition, and it's purely for regulations rather than the academic side. So why was there a need for foundation models? So we've seen a lot of models before that did particular very specific tasks. One example there is the YOLO object detection model. But then that was not enough. We had a lot of data coming out from the internet purely for the large language models, but also the video data and pictures and things like that on both medical and non-medical side. And so that was one need that we wanted to train on large scale of data. And another part was there was no, you couldn't do another task for that particular single model that was doing, for example, object detection, but it couldn't do classification. One example up there is that cat depth estimation model. So it could do depth estimation, but it couldn't say it was a cat. So that was an issue. So that's why we needed something that could be task agnostic. So what's the DNA of foundation models? So it has four main things. The architecture, output transformer, because that's what kicked off the whole thing, but things have moved on from transformer. We'll be talking about later on. So the main key innovations there was parallelization, global context, and scalability. The other half, the other main part was the pre-training, which was done on massive unlabeled data, so you didn't require any annotations. And then you could fine tune for a specific task. The fine tuning has two components there. Either you can adapt that to your data set directly, or you can fine tune for a particular task. So there's twofold things about fine tuning that you can think about. Self-supervised learning is another main component that basically triggered foundation models. And there has been a lot of advancements in self-supervised, started with contrastive, then there was masked classification or autoregressive methods. Then we had the Dino self-supervised learning, which is more of representation alignment rather than predicting any next token. So that's a difference in the self-supervised that's brought up the Dino v3 model. And then the emergent abilities. So zero-shot learning, few shot, chain of thought, and the new thing on language is atom of thought or something that came up last week. But then we need to know what are not foundation models. We've seen the traditional machine learning models are not foundation because they lack scale. There is no self-supervision there, and there is no transferability. Similarly to task-specific neural networks, they're only designed to do a particular task. Even one example down there is AlphaFold that came up for protein structure prediction. It uses transformer architecture, but it's not a foundation model because it's only predicting protein structure. You can't generalize to anything else. So they are single task focused, no emergent abilities on that side. Similarly, with other things like rule-based system or small language models, even less than 100 million parameters, they can't have any emergent abilities, so they are technically not foundation models. So let's look at the differences between these traditional models and foundation models. What is the categories where they are different? So architecture, we touched upon it, transformer with self-attention, and further things have moved on from transformer. There's a combination, hybrid architectures come up, which is different from traditional, where there is manual feature engineering. Training data, we said, learning paradigm is different, self-supervised pre-training and supervised fine-tuning, which is different in terms of other things like you're doing supervised or completely unsupervised. Similarly, task approach, general purpose for foundation versus a specific task for other models. Parallelization, we touched upon already. Parameter scale, I said, to trillions, still in thousands to millions for the other group. And transfer learning is another component there with inherent transfer learning within the model, which is different from the other ones. And what is an advantage here? You reduce the training time, the data efficiency is increased, and the task coverage is increased. So what led to convergence of these different things into foundation models? So there was architecture breakthrough, which happened a few years back with transformers. That has evolved into other things, vision transformers, masked autoencoders, and hybrid, convolutional network and transformer architectures have come up. So that is still is a backbone of these models. There is hardware advancements, a lot of hardware advancements since BERT came on early on. So the 2018 BERT training took 4 days. 2023 Dyno V2 took 3.3 days for training, but now we've dropped that clock timing for training because it's now more of GPU hours or GPU days rather than the actual clock days, because you can't relate those two dependent on the amount of hardware you use. So for Dyno V3, that example, it took 61,000 for 40 GPU hours. So that is equivalent to if we use 512 H100 hardware, it's 5 days in clock time. But they didn't actually use 512 H100. They don't mention anywhere in the paper. So they only say that's the GPU hours in the actual paper. Same thing with the data scale. So we've seen a boom in data scale, not just for text, also for image. So if you look at the bottom side, the data scale for Wikipedia is 100 GB. Then you come to Dyno V3's training data is 300 terabytes. And then the medical foundation model, which is Titan, the largest one till now, is 100 terabytes, still catching up behind. But it is growing. And the research goal have completely changed in terms of achieving some more general AI rather than very narrow AI models. Right, so we move on slightly different now. What is multimodal data in foundation models? So, what people mean is text plus image in general, but then there are lots of things within that. So there'll be plenty of categories that you can bring up, not just in natural side, but also in medical side of things. So it could be language plus vision, could be vision plus audio. Even within radiology, multiple types of images are regarded as different modalities. So it'll be multimodal within that particular domain. If you're looking at genomics and radiology, so that's already multimodal there. Even if you're looking at pathology slides, so there's text reports, and then the pathology slides is multimodal. So there's lots of things that you can combine, which is multimodal. And that's why it's not fixed to a particular type of domain. It could be within that domain, multiple things. So a few things we need to ask regarding a model, whether that is a foundation or not. So I put that on the table there. We talked about on all of that topics: data breadth, supervision, transfer, domain scope, interaction, system versus model. Is it a base model or is it a deployed system? That's a big question that Marc pointed out just now, and multimodality we mentioned. So I think it is time to sharpen that definition in 2021. And these are some of the examples. We will touch upon Dyno, as Marc mentioned, but those are some of the big foundation models, both on natural side as well as biomedical. We won't be able to go through all of that, but we'll go through one of them. And then now I hand over to David, go into some core aspects.